So in this lecture we're going to talk about some sort of, this is the miscellaneous debris stuff that doesn't really fit into anything else, but useful to know in sort of wrapping up our F# knowledge. I've decided to do the object-oriented session next instead of first because of time constraints. So in this lecture we're just going to look at some small little details which are highly useful and stuff that you can use every day, but which they're not really functional programming per se or anything. It's just language features that it's nice to know of. So first, access control. I haven't really mentioned access control at all. So whenever we do a module or inside a namespace or something, we are creating stuff. So far, all we've done, everything is public. So whatever you put inside a module, everybody can use. And that's usually not a big deal, in particular in functional programming, when you are dealing with immutable data anyhow. Is there any great deal of purpose of hiding your implementation? But sometimes it is, and it's actually, if you have a rather large module with loads of internal stuff that's not directly useful to anybody, actually marking explicitly what is public and what is private is a good idea, because then you know exactly what the interface to it is. So you go in and read the code, and as usually there is no documentation except the types and then the access modifier, and then you know immediately when you see private that those you don't even have to look at, because you only need to care about the public ones. So unless we explicitly say, everything is public. So let's do a module. Module hello, and we create a function. Let fx equals something. So this is now a public function as we are used to. But I can actually go in and I can say, well, okay, by saying let private f, this becomes private. So now f can only be used within this module. So any code inside the module can use it, and it's invisible from the outside, as you would expect. There's an alternative to private, which is slightly technical, but it's called internal. And that means that this f is usable within the same project. It's slightly broader than that. It's within the same assembly. So in the .NET world, when you create the .dll file of things, anything which ends up in the same .dll file can use this internal thing. So then you can have something which is private to anybody. So if you're making a library, you can have this thing which can be used all over the place in the library, but which is internal to the library, and nobody from the outside can use it. The consumers. Might be useful sometimes. I've never used it, but that's if you're a library writer, this is probably something that you might want to look into. Now, so this was at the sort of module level, and saying, okay, this is a function which is private, but of course I can have private types inside a module. Type private, or internal. Whenever I say private, I could say public or explicitly public or private or internal. Type private foo equals record type or union type or whatever. And now this type is only visible from inside this module. So we can use it inside the module. And that's okay. And yeah. But there's a case which is super useful. Really super useful. And that is having a public type but with a private constructor. So I'll show you how to do this. And then I'll explain why this is a good idea. So I can say type foo equals private. So now look, previously when I created a private type, it was type private foo, but now it's type foo equals private, and I can make it a record type and I can do whatever I want. Or I could say type var equals private case A of something or B of something else. Right, so what does this mean? Well, this means that this type is publicly exported from the module. It's completely visible inside your module. So you can do, it's like a normal type inside the module. But from outside of the module, you can see the type, you can see what it contains, but you can't create it. So you can only create these inside your module. Which means that now you have full control of how your type gets created. Because you don't let it loose. Nobody can create whatever. And this allows us to create smart constructors, where you can do all kinds of sanity checks on things. So for example, suppose we would do something like this. Type chord, if we for some reason would implement things like this, I would say type coordinate equals private A of, or C of float list. So I could say this, that okay, this is a list of floats. I call it coordinate, and I make it private. So now I can say make a function let mk3d chord, which takes a list of coordinates, which I will just call C, and I say okay. So this is a public function. It can be used from the outside. I can say if c.length equals 3, then C3, CC, right? Else fail with error, right? So now I can make sure that this will produce a list with 3 elements, or 2 elements, or 5 elements, or whatever, right? And this can be used inside the module. This can be used outside of the module. So I can call this function to generate a type of the right type. And the type is known, so once you have it, then you can just deal with it, whatever you want. But now you made sure that it conforms to your standard by using this smart constructor, which is just a function. It's just to produce it. And this is highly useful in a lot of places. We use these a lot. Okay. So that was access control. Check. Right, so there's a little thing with the F# type system which is going to bite you sooner or later. You're going to find out that what is this. And I'm just going to illustrate it with an example and then show you how to resolve it. So let's define a function add x y equals a plus x plus y. So in theory, this is now completely generalized. If you type this into Visual Studio, it will say that this is int. But that's a mistake. It just thinks it's going to be int. This plus is defined for ints and floats and doubles and complex and what have you. So we don't really know, but it's going to guess that this is going to be int. And now if I want to use this thing somewhere, I'm going to say let's call this a equals add 1 and 2. So now it's going to say, oh well, okay, these are clearly ints, so this is going to specialize this to ints, and then I can say, okay, let b equals add 1, 0, 2, 0, and this will now be a type error for no apparent reason. Like this is supposed to be a generic function, right? But what happens here is that the F# will look at this and they say, okay, I have no idea what these types are. And then you use it with ints and they say, now I know what the types are. And then it sets them once and for all. So now we know that, okay, this is int. And now we try to use it with floats, and that's clearly not a good idea. So the way to get around this problem is by using a little keyword, which is let inline add x, y, and problem is gone. Because now the compiler will inline take this definition here and just put it straight into the and then we can just use it with any number of ways we want. So when you end up with this situation where you have something which is generic and it get the type first bound to something, and then you try to reuse it with another type that is supposed to work, and you get an error, remember inline. The inline keyword. Yes, we have a question.
Would that also be the case if you made x and y explicitly generic types?
Yes.
You would also.
Yes, because the compiler resolves the type and says, okay, this is the type, and then so. There's something, this is a deep rabbit hole, but you can actually, it's kind of tricky to do it in F#, but it's possible. You can actually do something which is called rank n polymorphism, which allows you to write functions which accept a generic function, so that you give it a function which is explicitly generic to this function, and then it knows how to specialize it inside of itself. Yeah, that's a cool trick. So, but that's way beyond what we're going to talk about, because that requires all kinds of weird things like digging into how to do existential quantification and so on, and that's not fun. Oh, it's hugely fun, but it's not here, right? So that now we've seen that. So third little thing that to know about. Sometimes you will. All right, let me back up. In C# and in the rest of the .NET world, whenever you create an object from a class, you call a constructor on things. So suppose there is some, let's create some string object. So we would have something, a class called string, like this. And the way you would create it is that you would give it maybe a constructor with some value, hello, or some other way, or you would have an empty constructor. But this is basically let s how you create objects in F#. So whenever you're dealing with object-oriented code, you have like the name of the class, and then you parentheses add stuff, and you shouldn't have any space here. We'll talk more about this when we talk about objects. But this is how you create objects. Now in C#, you would have always the new keyword in front. Say, I want to create a new object of this. You can do this in F#, it's perfectly valid, but you don't have to. And most of the time we just skip the new keyword. But there is one case when you have to, you put in the new keyword, where you actually don't have to, but the compiler will complain to you if you don't. And that is if this particular object here, and this is not one of those, if they use resources like they need to clean up after themselves, which means that they implement the interface IDisposable. So for example, if it opens a file, it opens a database connection, it opens, so if it's an IDisposable, which actually, to be quite frank, when we're programming F#, we really don't care and don't know, except that when we type suddenly that create a new database something something, you will get a yellow wiggly line under your code. And then you need to know, it's an IDisposable, add the new keyword, and the wiggly line goes away, and we're happy. So for IDisposables, we need to have this new keyword. Why? I have no idea. I can't see that what good it does, but okay. And the code works if you skip it, like it's no problem. You can also use, instead of new, you can say use. Same thing. All right. Yes, so yeah, so in the last section, lecture, we talked about looping, and of course we talked about map, and we talked about filter, and we talked about fold, and before that we talked about explicit recursion, but of course we also have the for keyword. So we can say for I in, and like in Python, like some kind of object, whatever it might be, do, and then we can just use this I. But this is here an I enumerable. So any kind of object which implements this I enumerable interface, which you can do on your own objects when you define them, we can loop over them. So this could be a list, an array, a map, whatever, and we can just loop like this. But again, remember that map tells you a lot more about what's going on, and filter. But this might be quite a good alternative to fold, because folds are not super readable. I always do folds because I have a Haskell background, and then it's natural to fold over everything. But this is perfectly fine. Right. So then let's conclude this session with something which is quite special to F#. I don't really know many other languages that have this feature. And this is particularly useful if you are a programmer who deals with stuff which has units. So if you're a physicist or a chemist or an oceanographer or whatever, so you're dealing with physical problems typically. Well, I mean, you can use them wherever you want. In money, money. Like it's very important whether it's Norwegian kroner or mega Norwegian kroner, right? The NOK and NOK, or kilo NOK. In thousands of kroner, right? So these are important things, like what are the units? Or are they in dollars? So F# actually supports units of measure. And the nice thing about this is that you can define your units of measure and say, okay, this is defined this and this way. And then F# will actually do arithmetic on these units. So it will understand that how things match up. And it will prevent you from mixing pears and apples. So I have a very simple example here. So the way you do this is that you say, okay, we use this special annotation measure. And then we say type. And I'm going to do type centimeter. And that's it. I'm just not saying anything else. I'm just saying type centimeter. And then I can define a new type, and I'm just going to do like this to repeat the measure. And I say type centiliter. And now I can say centiliter is defined as centimeter cubed. Yeah? So now these two are connected via this centimeter thing. And then I can say, well, type cm2 to be, well, cm to the power of 2. Okay. So I can use these measures now. I can say, okay, let A, and I can give it an explicit type, say it's a float of centimeter 2.0, and then we can say let B equals a float of centiliter, and then we always go for the big one, so we're going to have 5 centiliters. And then we can say something like this, let C, I'm going to do it like this, equals B per A. And now it's going to give it automatically the unit, but it's probably not going to give it. So it should give, since we have this is B is centiliter, which is centimeter squared, and this is centimeter. It should give us this type. But the compiler isn't so clever, so it writes it out as CM3 divided by CM2 or by CM, and it's sort of all fine. But you can actually go in and give it an explicit if you want to have it sort of nicer and say that this is going to be float of CM2. If you flip these two, you get an error. And or if I try to do something like let D equals A plus B, those units cannot be combined. That's also an error. But these are just floats, so normally you would actually, so normally that would be perfectly fine. And now, of course, you can change this into dollars and this into euros, and so on and so on. And now you can make sure that whenever you add euros and euros and dollars, but you can never add euros and dollars and NOx because they are different units, and then you need to take very much care how to convert from one to the other. So this is a highly useful feature if you're dealing with these things and you need some extra type safety on things. And it's lightweight. Like you could achieve a lot of this by doing smart constructors and union types and so on, but this is much more lightweight and easy way. And especially since the compiler can simplify this type for us. So that's pretty cool. And that's it. Now we only have object-oriented programming in F#, a quick overview left, and then we can start looking at part 3. All right.